Welcome again, my friends and followers. Let us talk about condensation, heat transfer coefficient. How can we estimate the condensation heat transfer coefficient of fluids as they pass through the tubes? It is meant here to talk and present the condensation process when we have internal flow in the tubes. Let us go to some details of this subject. Dear friends and colleagues, we have arrived to the final part of this series of videos and lectures presented by Professor Ali Tarrad about the condensation of process in and its application in industry. We introduced the condensation process when it occurs uh, as external flow on the outside of tubes or internal flow uh, as condensation inside the tubes, vertical or horizontal, and how we can deal with the condensation and how can we predict the transfer coefficient on the tube bundle as well. And this part presents the final part of the condensation topic. And thank you for support and uh, subscribe to this channel. Uh, Please, if you haven't subscribed to this channel, I urge you to subscribe and you may activate the notification to receive more videos about different topics of heat transfer and energy and from this channel. And let us go to the content of this part, which will be an industrial application of the condensation inside horizontal tubes. And don't forget that we have in, introduced many examples from the industrial field when we are dealing with condensation. The practical case study which we are going to present in the present video is related to a condensation process in horizontal tube for refrigerant R134A at a pressure of 3 bar with the flow rate of 150 kilogram per hour and the quality or vapor quality of 0.8. So we have horizontal tube made of carbon steel with outside diameter 22.22 millimeter and inside diameter of 19.7 with a length of 2.5. Uh, the question is related, how can we calculate or estimate the condensation heat transfer coefficient of this process when we have the uh, refrigerant properties are listed in table 1 as shown in this table. We have the saturation temperature equal to 0.67 and the last row represents the critical pressure of Ferion 134A, which corresponds to 40.59 bar. and sigma L represents the surface tension of the liquid for the refrigerant 134. Solution for this case study is starting from estimating of the mass flux velocity, which corresponds to 136.7 kilogram per meter square second. I will use Ecker's et al. Correlation, which was presented in 1959 in the form of equation 3, and we start the calculation of the equivalent mass flux uh, velocity, G equivalent, which corresponds to 1049.74 kilogram per meter square second. And the equivalent Reynolds number depends on this value of mass flux velocity, which results in Reynolds equivalent equal to 76,029. Prandtl number for the liquid phase, we have to use the liquid thermal properties to be the Prandtl number of liquid equal 3.82. And depending on the limit of Reynolds number, then we have Reynolds number equivalent greater than 10 to power 4. Then, according to Eckers et al., C equal to 0.0265 and N equal to 0.8. If we put these or substitute these values in equation 2, then we will get a heat transfer coefficient of the condensation process to be 1596.44 watt per meter square Kelvin. This is the final results when we are using Kerr's equation. Summary of this practical case. Here in this table, I included the results when we are using Shah 1979 as reference number 7 and Shah in 2009 reference number 6, as they are listed and seated in the link below this video in the description box. Of course, these calculations are quite lengthy, therefore, I prefer just to put the final results of these correlations, and you may compare these values. And if you want to get more information about the procedure and we have got how we have got these values, you may go to the book entitled The Principles and the Practice of Heat Transfer to find more examples and the procedures for these calculations. Of course, we have to mention that in the thermal design of condensers, usually for the horizontal tube, any tube condensation, it is preferred to predict the annular flow heat transfer coefficient, where we have the shear controlled regime, and then the stratified flow, where we have the gravity is the dominant parameter, and we may get these values depending on the correlations available, and then we compare them and use the higher value to estimate the overall heat transfer coefficient of that condenser. Please go to these references and see how can you improve your knowledge about heat transfer and condensation in these applications. As a closure for the present video, in fact, this is the last part of this series of seminars and videos about condensation. And in this part, we passed through a case study for condensation in horizontal tubes, and we have selected Perion 134A for this process. Please, if you find that the content of these videos are useful to you, please subscribe and share them with your friends to achieve the critical goals from creating this channel. And I will see you in other topics of heat transfer and energy. Please don't forget to subscribe. You may find some important resources at um, in a link. They are available in the open literature, and some of them, of course, you have to find a way how to kind of get them. It is related to my book. Two books I have published about this subject, the heat transfer, and in the book entitled The Principles and the Practice of Heat Transfer, you may find more applications and correlations about this process and how can we deal with them. And of course, all of our correlations, or most of them, are related to pure fluids. And the process will be more complicated for mixtures, of course, when you are dealing with binary mixtures, for example. And I hope that you have enjoyed this series of videos about condensation, and see you soon in other topics. Bye bye.